Thank you very much, Chairman. Good afternoon, everyone. Thanks for your attention. So my topic today is discussion of the stress ratio effects on the fatigue delamination growth characterization in fiber reinforced composites structures. Firstly, I'm going to talk about the motivation for the talk. As we all know, it is quite important for the safe design of composite structures to characterize the cyclic fatigue behaviors of polymeric fiber composites. So, in the aircraft structures, despite designing using the no crack growth approach, we can still find lots of delamination damages on operational aircrafts. So one of the example is shown on this picture. So we can see here the severe delamination damages and even the detachment of the rudder at this aircraft. So in the consequence, in 2009, the U.S. Federal Aviation Administration, in its document AC 120-107B, reflected that the no crack growth approach should be modified, and in the same document, it introduced the slow crack growth approach for both composites and adhesively structures. However, in the slow crack growth approach, we required the delamination to be both slow and predictable, and this is the motivation for the research. So now the challenge for us is to find the way or the formulation to use in both ab initio design as well as the aircraft sustainment. So we often use the large artificial delamination tests in laboratory conditions to determine the intrinsic material properties. And we should also account for the following four factors: the R ratio effect, the naturally occurring small delaminations, and the scatter factors, as well as the conservative threshold values. However, in this presentation, I'm only going to address the issue 1, the R ratio effect. So here is some little background for metals first. So after Irwin found the crack tip stress field can be uniquely described by the stress intensity factor K, Paris reviewed in fatigue load, the crack growth rate was a function of the range of the stress intensity factor, delta K, and this led to the Werner-Paris equation here, where the delta K is the crack driving force. The R ratio load is defined as the minimum load and divided by the maximum load in one fatigue cycles. And we can see from the plots here, and for the same load magnitude, which is delta P, and the same the higher R ratio will give the test the higher maximum as well as the higher minimum load. So since the stress intensity factor is linearly proportional to load P, then we can also see that for the same value of delta K, a higher R ratio means the higher maximum and higher minimum values of the K. So here is the principle of the similitude of the crack growth for metals. For two different crack growths in the two specimens of the identical material with the same thickness and the same crack driving force, delta K, and with the same value of the K max, will grow at the same crack growth rate per cycle, the D at the end. And we extend this similitude principles with different R ratios. We can say for everything is the same, and with the higher R ratio, and the specimen, the crack, will grow at a faster crack growth rate. Now, this is the examples for the crack growth in metals. So we can see that with the higher R ratio, the R ratio to 0.7, which is the orange dots, and with the same delta k values, it growing faster than the r equal to 0.01, which is the blue dot. So thus we can conclude a higher R ratio means the higher values of dAdn at a given delta k and will grow faster. So now let's come back to the composites. So as we all know that the stress intensity factors is not quite good to describe the stress field near the crack for orthotropic materials such as composites. So people usually use the strain energy release rate, the G. So by analog to the use of delta K's for metals, many researchers and practitioners have used delta G when characterizing the fatigue performance in composites. And the delta G here is the crack driving force for composites performance. Then by the analog for the metal principle of similitude, we have the principle of similitude for composites. And generally, everything is the same except the changing the crack driving force from delta K to delta G and the K max to the G max. So we can also say at the different R ratio cases, so with the same delta G's, then the crack in the specimen subject to the higher R ratio will grow at a faster dAdn values for the composite. Now, let's look at what happened in the real test. So we're plotting the dAdn against the delta G's. We can say with increase the R ratio, which also means increase the mean stress, we can find the delamination growth rate is decreasing for the same delta G because the curve is moving to the right hand side with the increase of R ratio, where the black dots is R equal to 0.02 and red is R equal to 0.05 and blue is R equal to 0.06 for those who couldn't see. And there are lots of other examples for this situation. So what happened for the delta G and the crack driving force? So if we rewrite the delta G term in terms of R, so we can see it's proportional to the 1 minus R squared, and the R effect is actually being minimized as it's usually between 0 and 1. So back to 1965, the C. Paris and Irwin extended the metal solutions to a crack in orthotropic composites, and they find that the near tip stress field was described by square root of G. So it's logical extension for Paris laws to composites to using the delta square root G as the crack driving force, which we defined in the equation. So now we note the different forms of the two equations for delta G and the delta square root of G. So this one is proportional to 1 minus R instead of the 1 minus R squared. Now I'm going to present some test results for different delamination modes and the test specimens they used in different modes. So mode 1 delamination will be using a double cantilever beam. Mode 2 delamination is end-notched flexure. And mixed mode 1-2 delamination will be used the crack left shear specimens. Firstly, look at the mode 1 delamination for double cantilever beam test. And we can see the plot at the left hand side, its dAdn is plot against the delta G term, and the right hand side is dAdn plot against the delta squared over G. So we can see from the left hand side, the increasing R ratio and the delamination growth rate will decrease for the same delta G. But by plotting the same information within the same Paris-Irwin solution, delta squared over G, we can see the blue dots is R 0.7, which means the highest the R ratio will go faster than those with lower R ratio. Now that's the mode 2 test. So we can see that all the tests with different R ratio collapsed for most of the time, but we believe it's unacceptable as there are still many other materials is little R ratio dependent. But compared with this plot against the delta G, which shows the incorrect material dependencies. Now this is the mixed mode 1-2 cases. Again, by using the C-Paris-Irwin's solutions, delta square root of G's, we can see the increasing of the R ratio from right to the left with the increasing of the lamination rate. So for the conclusion, in the topic I present, the delta G is widely being used as the driving force characterization, the delamination growth in composites nowadays. But we find there is some incorrectly suggestions of increasing the mean stress would result in a slower delamination growth rate by using the DADN plot against the delta G. And then I introduced the C-Paris-Irwin solutions and lead to delta square root of G's. So by plot everything into the delta square root of G's, the anomalies observed when studying the effect of the R ratio, it will be removed. Yeah, that's all the presentation. Thank you very much.